Welcome to the 6th lecture of this course on basic building blocks of microwave engineering. In last 5 lectures, we have developed the microwave transmission model. We saw the concept of modes, then we have seen what are the fundamental modes. There are 3 fundamental modes, TM, TM, and also we have characterized them, and then we have found how to deal with losses in microwave circuits. Now, that concept today we will apply on the transmission structure which carries the microwave signal, that is the microwave transmission structure. Now, loosely sometimes we call this structure transmission line, but in microwave engineering we give a particular connotation to the word transmission line. Basically, a transmission line is a line which supports TM line, though actually a TM line can also support other TM lines, like a coaxial line, it supports TM mode, T mode, TM mode, but generally when we say sometimes the meaning of transmission line means a structure which supports only TM mode of propagation, and similarly we say waveguide is a transmission structure which supports non-TM modes, that is either T or TM modes. But in real practice a waveguide cannot transport TM mode, but the reverse, that means a 2 conductor line that can support all the things. So, that is why we give special name to each of the structure and see what type of mode propagates to that, and find out the field structure and other parameters associated with that mode propagation. So, the first in that today we will see a coaxial line. A coaxial line is, you can see, it is a general 2 conductor transmission line. We have 2 cylinders of infinite length, because transmission line means it is of a quite good amount of length in terms of the wavelength. So, we have 2 conductors, and if the 2 conductors are placed coaxially, that means their axis is same, but obviously their radius is different, then that is called a coaxial line. So, in the diagram you can see a 2 conductor transmission line. There is a inner conductor, and coaxially with that inner conductor there is an outer conductor. The axis is generally its convenience or customary to take the axis of this coaxial system to be Z. So, that means the transverse plane will be XY plane, or we will use the cylindrical coordinates for this type of cylindrical structure, and in that case it will be rho phi plane, and Z is the longitudinal plane. So, this is the coaxial line geometry. As I was saying, that we have shown here the Cartesian thing, but actually we will be describing this coaxial line analysis or fields in terms of rho phi. Rho is the radial direction, phi is the azimuthal direction, and Z is the longitudinal direction. Generally the outer conductor is grounded, that is why you see its potential is shown as V is equal to 0. Usually that is the practice, that the outer conductor is grounded and the inner conductor is given a potential. So, in this case we are denoting it by V naught, a fixed potential. So, there is a charge distribution in the inner conductor, this inner conductor, later we will see pictures that this inner conductor comes out, and this inner conductor is connected generally to the any load etc. Like in antenna we connect it to the load, in the source side we connect it to the one end of the source, the other end is the outer conductor generally that is connected to ground. So, in a single ended system, the outer conductor is grounded and the inner conductor is connected to the active line. Now, we will see as we have developed the TEM mode analysis. So, coaxial line we know it it supports TEM mode fundamentally, though it can support higher order modes also, but its dominant mode is TEM mode, and TEM mode starts from DC value that we have already seen, and we have seen that in case of TEM line we can, the field distribution is quasi static. So, we can, though it is a dynamic case, TEM is a dynamic EM field variation, but we can still use the concept of the scalar potential function phi, and that follows Laplace's equation. In the, it is a transverse Laplacian operator that we have seen. So, that one it follows Laplace's equation. So, that means the starting point of this field analysis, that means derivation of the electric and magnetic field, starts from that in the coaxial line, within the coaxial line structure, this Laplace equation in the transverse Laplacian operator, not the normal or ordinary Laplacian operator does not have t. This is a two dimensional Laplacian, that is why Laplacian operator with a t is reminding transverse Laplacian. So, that equal to 0. This is the Laplace equation, this should be obeyed. So, we will solve this equation, and from this we will determine the voltage and current, and from voltage and current we can go back to the electric field and magnetic field etc. So, as the structure is cylindrical, so we can switch over to cylindrical coordinates, so that the transmission line coax, its geometry falls on the constant surfaces, constant coordinate surfaces of the cylindrical coordinate. So, the Laplacian operator that in cylindrical coordinate will be only have rho and phi variation. So, that is why you see the del rho and phi variation. Now, as before, this potential function we separate into two variables, two functions of single variable. So, the potential function which is a function of both rho variable and phi variable, that we are writing as f rho into g phi. This is only, f is only a function of rho, g is only a function of phi. So, this if we put in this potential Laplace equation, then we get this equation. These are all mathematical details, these will be uploaded in the site. So, you need not you try to understand, just we are going the same steps that we have done in previous case also. Then in this case you will have to divide by this, and that is why you will get the that equation. Now, you subject it to the boundary condition. Now, what is the boundary condition? Boundary condition is sorry, let me see the previous slide. So, what will be the boundary condition? This inner conductor, this red structure, this is a metallic structure. So, we can say that tangential field is here azimuthal direction, that means in the unit vector along the phi cap direction. So, there, so that means when rho is equal to a, this is generally called a, the inner diameter, inner radius of the inner conductor, radius of the inner conductor. So, that means that rho is equal to a, we will say that the tangential field is 0, because this is a conductor. On conductor we know the boundary condition is tangential electric field is 0. Similarly, here that, or in terms of potential we can say that at rho is equal to A, the potential will be V is equal to V naught, and at rho is equal to B, that means on the outer conductor the potential is 0. So, since we are here on the Laplace equation potential function, so potential boundary conditions are that inner conductor the potential is V naught, outer conductor potential is 0. So, that is written there, that phi, this is the potential at A for all phi's, because everywhere on the surface it is V naught tangential thing, and then this also the potential for any azimuth, but for the on the outer conductor it is 0. So, these are the two boundary condition. So, you see that these two equations 29 and 30, they are that this left hand in 29 the left hand side, that is a pure function of rho only, but that plus this one, that is 0, that is a constant. That means a function of rho plus a function of phi, their sum is a constant. This is possible only if this side is equal to a constant that we are naming as k rho square. Rho is a subscript, but actually this whole thing is a constant. Similarly, this is a constant. Now, what will be the solution of this one? You see that we are, g is a function of phi, we are double differentiating it with phi. So, that double differentiation is equal to this function into some constant. That means that is double differentiation also is producing a function which is the same function. Now, this from our knowledge of differential equation, we know that this is possible only if we have either a cosine or sinusoidal variation. So, that is why the general solution of this equation will be that g phi is a cosine function plus a sine function. Now, this phi, you know that a phi, that means in a cylindrical coordinate, the azimuthal coordinate phi, that is an angle. So, that has a periodicity of 2 pi. So, any value of phi if I take, if I add 2 pi to that, it will be of the same value. So, we demand that g phi also should be periodic in phi with a period 2 pi. So, that is possible if this constant k phi becomes an integer, because then only cos of some value, some integer into the angle. So, if I change that angle by 2 pi, so that will be multiplied by k phi. So, 2 pi n, some n is an integer. So, k phi should be something like an integer, then only this is possible. So, this is the first thing, that k phi needs to be an integer. Then we have seen that boundary condition of the phi function, that is the potential functions V and V naught, they are on inner conductor for any value of phi, the potential is V naught. Similarly, on outer conductor the potential for any value of phi is 0. So, boundary conditions are invariant to phi. So, that means we demand that the potential function should also be invariant to phi. Now, how that is possible? A potential function invariant to phi is not possible, because it is a cos and sine function. Now, only way it can go there, that is if k phi becomes 0, but if it is k phi becomes 0, then cos of this, that will be a. So, a should be equal to 1, and sine k phi, if it is 0, then obviously this whatever may be the value of b, this whole thing will be 0. So, the solution is that a is equal to 1, k phi is equal to 0. Now, we come to the solution of k rho, the determination of k rho. Now, So, here we put that value, and from that this is a just second order differential. So, you know how to solve it. It will come as the f function of rho, that will be some logarithmic function. Now, applying boundary condition, we get the value of the two constants c and d, that will be like this. This c and d was our solutions. So, c and d we got as this, and from that the potential function can be determined, that is equal to V naught ln b by rho by ln b by a. So, you see that it is a function, potential is a function of, it is not a function of phi azimuthal angle, but it is a function of the radial distance. Where is it? Because of the presence of this radial thing. So, potential is changing with radial thing, that we have seen that at rho is equal to a, it is taking the value of V naught. Let us see that if we put rho is equal to a, then this becomes ln b by a, this becomes ln b by a, whole thing is 1. So, phi at rho is equal to a, that is V naught. So, correct. Similarly, another boundary condition is that at rho is equal to b, I should have this potential function should be 0. Put it here, that if I put b, it is ln b by b, that is 1, ln 1, ln 1 is 0. So, that is why this phi potential function again becomes 0. So, boundary condition is satisfied, and this is our solution of potential function. Once we know potential function, we can find the transverse electric field. These expressions we have derived earlier in case of quasi TEM analysis. So, you just put that gradient of this potential is the electric field, transverse electric field. So, if you do that in the cylindrical coordinate, we get that electric field, transverse electric field is rho directed. Transverse electric field is rho directed. It is a function of rho, but not a function of phi. That is why you see that its direction is rho, also it is dependent on rho. That is why rho is present in the expression, no phi. So, it is always pointing in the radial direction, transverse electric field is radially going out, and that was the transverse electric field. The total electric field, we need to put the longitudinal variation, that we know is wave variation e to the power minus j beta z. So, it is transverse component into e to the power minus j beta z. This is the solution of electric field phasor. Now, once we know electric field phasor, we can find the potential difference between the two conductors V12. So, from A to B if we go, then we know V12, that will be the minus integration of E dot dl. So, if you do that integration, the V12, that means the difference between the or potential difference of the inner conductor with respect to the outer conductor, that will be V naught. That is obvious from the thing also, and also from the field theory, from our field solution also it is coming. Now, similarly, you can find out the magnetic field. You will have to find the transverse component of H as in equation 36. Then you find out what is the total electric field phasor. That means, this is the transverse component H tilde. So, you will have to take the z variation e to the power minus j beta z, and the full magnetic field phasor is written like this. Now, once you know magnetic field, you know how to calculate the current, because from the magnetic field we can easily find the current, and that will be given by this. So, this is the on a current is on a loop. So, you will have to take that loop direction, and that becomes this. So, it is nothing but the, you see, the it is V naught by rho ln V that thing. So, 2 pi into this, that is 2 pi into the magnetic field, that is equal to I naught. Now, characteristic impedance, this is a transmission line. So, it will have a characteristic impedance, and characteristic impedance is the ratio of voltage by current in a TEM line. For TEM, we have seen that characteristic impedance does not have a meaning, that we have already discussed, but we have wave impedance for all. But let us calculate, since it is a coaxial line, we will have to calculate the characteristic impedance, that is V by I, and that is eta ln V by A by 2A. So, you see that it is eta is the intrinsic impedance. Now, that is, you can have some value of it chosen. So, that is more than 2 into 3.14. So, roughly 6 or roughly 7. So, more than 7 if the ln V by A is, then you get that Z naught is more than eta, otherwise Z naught is less. So, characteristic impedance of coax, you can choose like this, or if the characteristic impedance is specified, you can immediately find out that what will be the value of this ln V by A for a given eta. So, this characteristic impedance depends on the coax geometry by wave impedance, but eta is independent of the geometry. Obviously, eta is the intrinsic impedance of free space, it does not depend on the geometry. Then, what is the power carried by coax? We have already seen when we did loss analysis, how to do what is power. Power carried by an electric field is the pointing vector, this side is pointing vector, then you will have to integrate it over a surface on which the power is flowing. So, pointing vector into dot ds. So, that if you do in cylindrical coordinate, you get it is half V naught I naught square, I naught conjugate. So, this power, remember that in the coax, power flows entirely by fields. So, there is otherwise no circuit, because where is the power? Power is between the two conductors, the electric and magnetic field is there, and that field is making the power flow possible. That is wave is taking that power. Power is not carried by the conductors. Conductors do not carry the current. It is not the conduction current type of thing. It is inside the wave, through the medium between the two conductors, that is the either free space or dielectric, through that the power is flowing. So, that space between the two conductors, that carried the power. Now, coaxial line can also support higher order modes like T and TM modes, but the modes that in a coax, these modes, if we see their beta, it becomes an imaginary thing. Now, if beta is imaginary for any wave, we call that evanescent wave, because it actually, instead of carrying the power in the wave form, actually it attenuates the wave. So, evanescent waves, when they are produced after traveling certain distance, they are cut off due to these, because they have a lossy structure. So, evanescent, this in coax, whatever TEM modes we get, those are evanescent mode. So, that means they do not take the real power with them, and they give only reactive effect near sources or discontinuities. So, these evanescent modes are produced, because to produce higher order modes, either when we are near the place where the source is putting the power to the transmission line or coax, there is a discontinuity. So, there these evanescent modes are present, there are these higher order modes present, but if we are a bit away from the source, roughly 5 lambda, 10 lambda distance, then this evanescent modes die down, only the TEM mode propagates there. Similarly, near the load side, or if within the coax, we suppose we join two coaxes together. Now, obviously, any joining by mechanical thing, so that will create a discontinuity, or if the coax, suppose one larger coax and one smaller coax, if I am connecting, so that will be problem, and there will be discontinuity, and that time these modes will come. Now, there are by doing the mathematics that we have developed in case of T and TM modes, you can find the cutoff frequencies. You should be aware of that, because transport of power, you should see that when you are trying to send power through a coax, unnecessarily those TE, TM modes, if they come, they will take some power which you won't be able to extract at the load end, because at the load end we will be extracting the TM mode, because this TE, TM mode, they are not able to propagate longer distance through coax. They can propagate in waveguides. Waveguides are meant for TE, TM mode propagation. So, there they can go for longer distance. So, you should be aware that in your coax, these higher order modes TE, TM are not present. So, you should design your coax geometry by that way. Now, this is the cutoff wave number. So, dominant T11 mode, this is suppose one of the first mode that comes as a higher order mode T11. So, this is the ratio B by A, outer conductor radius by inner conductor radius. Basically, this ratio is very important. You have noticed, I think, all the voltage, current, fields, etc., all are coming in terms of this ratio. So, this ratio says that what are the frequencies at which this will take place. So, suppose I have the B by A ratio, generally we take B by A ratio something like 3.6, the reason we will see later, but so there I can see that okay, the T11 modes will come at this value of A. So, we will choose A so that it does not come. That means, if I choose A value a bit less than this A value given by this, then I will be able to find out. Kc is, you remember, the cutoff wave number. So, cutoff wave number, that depends on both the frequency of operation, medium parameters, as well as the, for in case of TM mode, the beta is 0, phase constant, or beta is equal to k, but in other cases there is a beta. So, that Kc is there finite. So, you can calculate that, and it is normalized to that. So, for dominant mode, these are the values. Kc is equal to 2 by A plus B. So, based on that you can find out the cutoff frequency. So, cutoff frequency will be this, and here we have shown that if we go on increasing the frequency, so where first you will see a T11 mode in coax, then it will be a TM01 mode, then a T21 mode, then here if you go on increasing further, here two modes, one T, one TM, they starts propagating, and then if you go further, you have T31, then you have TMT1, etc. So, this shows that which modes are propagating. So, decide on the frequency. Suppose your frequency this, that means you know that apart from TM, you will also have these all three modes present. You need not worry about this, because you are here. If you are here, then you need not worry about these two, but you need to worry about this. Okay. So, this is the TM field lines. You see the electric fields are these solid lines. So, as we have seen that they are radially. So, this is the inner conductor, this is the outer conductor. You see from inner conductor to outer conductor everywhere, it is radially outward directed, and the magnetic field is the circular lines. So, that means, at this point what is the magnetic field? You need to take a tangent to that, because these are actually lines, strip lines, sorry, they are called field lines. Now, tangential to that at any point gives you the tangent direction is the field direction. So, that means this magnetic field is azimuthally directed, whereas the you see the electric field line of a T11 mode in the same coax, it is not exactly radial. So, it has some parabolic shape you see at the 2 points, otherwise also it is somewhere it also has a curvature at all the points, whereas magnetic fields looks like same. So, that was the coaxial line. We have coax from lot of analysis. In the transmission line theory you have come across, we have seen here from the field theory viewpoint also the same field structure etc. You have seen that this field structure you have earlier in your transmission line classes derived, that this is the electric field and magnetic field, but from voltage current concept here also we came there and see that the electric field lines are like this etc. So, this is we have demonstrated that TEM mode theory whatever we have developed, that if you apply you can calculate the fields as well as various parameters like characteristic impedance etc. of the. Okay. Thank you.